Welcome, everybody. My name is John Lakos. I want to say right at the start that there are two sessions, and we're not going to talk about inheritance at all, really, in the first session. So if all you want to know about is inheritance, then unfortunately, you're going to have to go to the second session. However, all of the information I present here will, most of it, will be very useful in discussing the inheritance part, which is a bit more advanced. What's more relevant is that the C++ Standards Committee is working on introducing contracts into C++ for the next generation. So a lot of the information here is a good foundation for understanding what they have to go through to come up with the appropriate syntax and constructs and such. So that's what this is. Okay, so here's our wonderful copyright notice. I think this is just because I have to put it up, but I think that's good enough. Here's the abstract for people who are going to be viewing this. If they want to read what we're going to be covering, that's good, but you guys that are here have already pretty much decided to come here, so this, you'll see what happens. Okay, so what's the problem? So in general, I like to talk about working on large-scale C++ systems, and it's a multi-dimensional discipline, and it requires designing with logical and physical elements. Now, when I first came up, oh, that's no good. I hope this doesn't do this throughout the, can I turn that off? I apologize for this. There must be a way to turn that off. Well, if it comes up again, I'm going to have to do some surgery. Anyway, the ability to isolate and modularize logical functionality, and that's what we normally think of when we write programs, but we need to place them, locate them in separate physical units. And these units, these fine-grained physical units, are something I call components. And we'll talk a little bit about this in the very introduction of the talk. We need to delineate in English, or whatever language of choice, but preferably in English, to the client what this component does, and then we need to make sure that the physical dependencies that result from implementing it are acyclic, have good properties, that they don't become a big ball of mud. And there are numerous logical and physical design rules that govern sound design, and all of these things come to play when we're designing large systems. So I wanted to say that because that's sort of the larger context of what I do. So what we're going to do in this talk is we're going to review components. So you know what I mean by a component. This is kind of just basics of design. It really is the least relevant to what we're going to be talking about in the second session. Then we're going to talk about interfaces and contracts. This is hugely important to what we're going to be talking about in the second session. Another thing is a very specific kind of contract, which is a narrow contract, and it admits what we call undefined behavior, whereas wide contracts don't. We're going to talk about that. And then finally, we'll get to the purpose of the talk, which is in the second half. The reason I normally would try to give this talk in slightly less time and speak very quickly, normally I have a tremendous number of slides per minute. And I'm trying not to do that this time, trying to be a little calmer. So if you came to see the largest number of slides presented in a unit of time, that is not what's going to happen this time. I have under 500 slides for both sessions combined. and so this is going to go very slowly by comparison. Okay. So let's start with components. So this is the iconography that I like to use. I have physical things, those are rectangles, and I have logical things, those are ellipses. And we want them to come together in a coherent manner so that the logical content is embodied in a physical module called a component. So logical means classes and functions, and physical means files and libraries, basically. Does that sound fairly familiar, or this is news to me? Oh, okay, just trying to get a sense. Anyway, so each component contains some amount of logical content. And I'm using the new old Booch notation, I think, here. This is the symbols, the little circle with the line through it is users in the interface icon. So that's just to give an example of what something might look like. It's not serious. But anyway, each one of these embodies a certain amount of logical content. And you can see that there's a hierarchy here. And the things at the lower level are lower level components. And things higher level are higher level components. And the higher level components can depend on the lower level components, and so on. So here's a component. It consists of an implementation file and a header file. And I trust when people deliver libraries, they deliver whatever they're delivering in a .cpp file with a corresponding .h file in name so that people can include that and then properly use what's in the implementation without recreating the declarations locally and making all kinds of mistakes. Right? So that's the way we deliver software in terms of components. And then we have this thing called the test driver. And the test driver is what we use to exercise the component and make sure it does what we claim it does in English. Okay? This is our fundamental unit of design. Everything that's in any library we ship looks like this. And by the way, if you were to want to go look at this for real, you can Google Bloomberg, GitHub, BDE, these kinds of things, and you can find our open source libraries that are built this way. All right. So a component is more than just a .h.cpp pair. It has certain properties. There are 4 properties that it must have to be a proper component. And the first one is that the CPP file includes its H file as the first substantive line of code. Now, this is a very important property. It's the first property. Why is it, do you think, that we want to include the H file as the first substantive line of code in the corresponding CPP file? Anybody? Ensure that everything is included in the H file. Everything. I'm sorry?
Everything it needs.
What is it?
Everything the H file needs.
Is included. It needs to do what? What it needs to do what? Compile. Everything is in the .h file that the .h file needs to compile in isolation. So by doing this, we ensure that we're not relying on some other include, so when the client includes the H file, it doesn't compile because the client didn't already include, let's say, IOStream or something like that. Okay? So that's right. There are 3 other, oh, I forgot to mention, this is true even if the .cpp file would otherwise be empty, because we want to make sure that the .h file does in fact compile, and more, it's the case that compilers do some compilation or some analysis of template code even though it's not instantiated. So if, for example, I believe it's in the client compiler, if you have something that there's no instantiation is possible because there's some defect, then the client compiler will complain. That's the kind of thing that I'm looking for. But even if it's just something like missing a semicolon or whatever, I don't care. I want it to get compiled, and I wanted to get it compiled before I ship it off to the client. Even though we're going to test it thoroughly, I still feel this is an important first step. So here are the other 4 properties. And the thing is, I'm not actually going to talk about them because it would take like 20 minutes, and there's a lot of stuff there. So just in a nutshell, the first one is really to avoid global namespace pollution. They're all very much related. The second one is to achieve logical physical modularity or coherence, meaning that the logical content that I'm implementing in this component is in fact implemented in this component, or it properly depends on something else that is a component. And the third one really is I want to be able to extract without having to compile the code using, let's say something like Clang or whatever. I want to be able to extract the physical dependencies among the components that I have through the #include directive. So the envelope of #include directives is going to give me what I need. If we follow all these properties, then we get some very good results. So there's a lot more to this story. Now, this particular talk has 975 slides. So I can't really talk about this advanced levelization techniques talk, but there is a talk on that, and I will be giving this talk at CPPCon in September, hopefully. All right, next, logical relationships. Here we have a shape, a polygon, a point, and a point list. Now the shape is an abstract class, so we're going to see a little inheritance thing going on here. The point list link is a private class. It is not supposed to be used outside the component that defines it. And we know this because in our nomenclature, when there's an underscore in a class name, it makes it private to the component it's in. And the leading part will be the name of the component base. So we have point list, and then we have point list link. Okay. Now, to describe public inheritance, we use an arrow, and this is typical, right? So a polygon is a shape, and we have uses in the interface, and a polygon uses point in its interface because there are member functions in Polygon that take in their interface a point or return a point. An example would be add vertex. So Polygon uses point in its interface. Pointless, clearly it's got to be able to insert points into the point list, and the point list link also needs to be able to use a point in its interface. So you notice here we have these logical relationships. Then we have uses in the implementation, which means it's not programmatically known that this thing is used. You can't tell, but nonetheless it is in fact used. And so here's an example where Polygon uses point list in its implementation. For example, it might have it as a data member. It doesn't matter whether it holds a pointer or whether it's embedded, it still uses in the implementation. And then it turns out also that point list will use point list link in the implementation, but that's less interesting because they're co-located. So the logical dependency or relationship doesn't affect the physical dependencies. Okay? Then we have this very special one where the logical relationship does not affect physical dependencies even though it spans physical units, and that's called uses in name only. And if you look at something like shape, because it has pure virtual functions, it doesn't need to include point at all. It can forward declare point, and that works. So this is an example where it doesn't affect the physical dependencies. All right. So then we have these implied dependencies. Uses in the interface and uses in the implementation all imply physical dependencies when they cross component boundaries. So we use the big fat arrow from box to box now, and we observe that Polygon is a shape, so Polygon's component depends on shape's component. Polygon uses point in the interface, therefore Polygon's component depends on point's component. And the same for point list. And then finally, Polygon uses point list in the implementation, and so there is a physical dependency there. Now, once you have these physical dependency arrows, you can extract level numbers. And it's done simply by something that doesn't depend on anything else locally is at level 1. Okay? Now, shape turns out, because of this strange relationship, is also at level 1. Now, if we look at point list depends on something at level 1, so it's at level 2. And then Polygon depends on something at level 1 and something at level 2, but the highest one that it depends on defines its level number, not the sum, and so the answer is 3. So then if I had something that depended on Polygon, it would be at least at level 4 unless it depended on something else at a higher level. All right. Essential physical design rules. We have many rules, but there are 2 that are very, very important. So what do you think the 2 most important design rules are for large projects, or any projects for that matter, but large projects especially? I heard acyclic, no cyclic physical dependencies. That is the #1 rule. There is another rule that's surprisingly important, and the reason it's important is it's architectural. It's not something you can patch. For example, if I depend on or if I include something and it includes something else, and so I'm relying on that transitive include, and for whatever reason the one that I'm relying or including stops including the other thing that I'm using, it won't compile because I didn't include what I should have. You're supposed to include what you use. But you can fix that. That's easy. This one and the next one you can't fix. And so what is the second important design rule? All right, well, if you might not recall the book that I released 20 years ago, but it was the end of chapter 3. It is no long-distance friendship. No private access is allowed to span the component boundary. That means that the unit of logical encapsulation is nested within a unit of physical encapsulation. Okay, so those are the two rules. If you get those right, you're way ahead of the game. And are there any questions, by the way? Because we just finished the review of the stuff that is least likely to affect the second talk. We're about to move on to things that are more likely to do that. And I'm just going to put my watch here because I have a feeling I might be going a little slowly. Does it sound like the right pace? Should it go a little faster? What do you think? Faster? Okay. Fair enough. It can go faster. So here's some questions. Take a look at these if they put anything into your mind that you want to ask, or any questions at all? Yes.
Yeah, I don't have an example off the top of my head, but logical design is essentially non-hierarchical, whereas physical design is really difficult to get out of a hierarchical structure. And given the two rules you just gave, isn't there going to be a conflict that includes non-hierarchical logical design?
Okay, so Jim just said we have physical design is hierarchical. Yes, it is. And logical design is, you're saying, inherently not hierarchical.
Not inherently, because there are places where there are non-hierarchical constructs to be able to express what a logical design.
Okay, so what was said was there are situations where you have cyclic logical relationships. And this particular comes in with algebraic structures where you say I have some sort of a graph, right? And there are techniques for breaking the physical dependencies while preserving the logical ones. Those are levelization techniques. But it can be, but it's not intuitive. You have to struggle for it so that you have your hierarchical physical rendering, which is extremely important for large-scale development. So you have to put in real brain cells to map your logical design onto the physical hierarchy. And that is something that you don't do natively. You have to think about it. Once you start doing it, it becomes more natural and the two become synergistic. But it's a very good point. And you know, as I said, there's a talk in here that talks about how to do. I mean, not in here, but there is a talk that talks about how to do it, and there's also a chapter in a book that talks how to do it, and so you can look at that. But I think it's a very fine point. Anybody else? Okay. So picking this up a little bit, interfaces and contracts. We're going to talk about interfaces and contracts for a function, for a class, and for a component. Okay? So first, is this an interface or a contract? It's an interface. And these are the types that are used in the interface. So we saw that little bubble? Here we go. This is a contract. We'll get back to this. You see there's a very big difference. One is in English and one is in code. Okay. Here's a class. This is the public interface. Okay? This is part of the contract for the class and happens to state an invariant. Okay? Here is function level documentation that states the contract for the function itself. Here's more contract. Okay? Here's a component. In a component, we have a class and perhaps we have some free operators. So this is the public interface of the component. It's what clients of the component would touch. Okay? More contract for the free operator, and again, more contract for the free operator. Okay? All right. So, preconditions and postconditions. This should not be a surprise to many, but let's talk about what it is. Here I have a function, a free function. Is this a precondition or a postcondition? Precondition, good. And for a function like this, it's how we restrict the syntactically legal inputs. So, in other words, if you can put in any int into the interface, but the function is designed to take only non-negative numbers, the precondition would tell you, don't put in -5, put in 0 or higher. If you put in -5, no good. All right, what is this? Precondition or postcondition? Okay, it's postcondition. And basically, it's what the function returns. Now, for an object, there's more to the story. Preconditions must be true of both object state and method inputs, otherwise the behavior is undefined. So here's another exercise. I want to make sure that we're on the same page. Think of a standard vector, std vector. Can you think of a function on standard vector that has a precondition that does not depend on the value of an argument? Front? Excellent. So that's a good example. Postcondition is what must happen as a function of object state or if all the inputs are satisfied. Now, to be clear, there are preconditions that can involve parameters and the object state. Again, can you think on vector something that involves both object state and the input? Index operator, correct. Very good. Now, the postconditions, another name for them is essential behavior, and I would be surprised if there were even 2 people in the room that don't know Kevlin Henney. He's the one that pointed this out to me when I gave a similar talk in like 2008. So it's a good point to realize that while a postcondition is a static property after the function executes, the essential behavior is part of what the function promises to do. For example, if it's going to work in logarithmic time relative to the size, then that's part of essential behavior, but it's not a postcondition. Okay. So we have undefined behavior and we have not undefined behavior. And not undefined behavior breaks into 2 categories, essential behavior and neither undefined nor essential. So to see if we understand that gray area, let's take a look at this contract. I'm going to just read it. Format this object to the specified output stream at the absolute value of the optionally specified indentation level and return a reference to stream. If level is specified, optionally specify spaces per level, the number of spaces per indentation level for this and all of its nested objects. If level is negative, suppress indentation of the first line. If spaces per level is negative, format the entire output on one line, suppressing all but the initial indentation is governed by level. If stream is not valid on entry, this operation has no effect. So, is there any undefined behavior?
Just a question of clarification.
Yes.
Are you restricting behavior to things that are externally observable?
Am I restricting behavior to things that are externally observable?
I'm thinking back to 2 or 3 slides ago, we were talking about object state, and Kenny's claim that state is subordinate to behavior. That's true only if the state is externally observable.
It's an interesting point that will come up, what you're talking about in the second talk. There'll actually be slides that make that point.
I'll leave it till then.
Fair enough. This is payback for when I started my career because I attended his talk, and I also asked a lot of questions. Okay. So this is a hint. Any non-essential behavior, and I'm putting this out there as a hint because there is an answer that exists on the last line. It says if stream is not valid on entry, this operation has no effect. What if it is valid on entry, but it somehow goes bad during the operation? Do we know exactly what happens? It doesn't say. So this is an example where it's probably not going to blow up. That's a good thing, because if it were going to blow up, we should tell people it's going to blow up. So it probably doesn't blow up, but we don't know exactly how many characters get put out. So that's an example of non-essential behavior. It's neither undefined nor is it essential. But there's another one that's even bigger. So think about this. Did we say anywhere what the format of the output looks like down to the, let's say, whether it's a square bracket or a curly brace that deals with the nesting level? See, we never really said what it looks like. We just sort of talked around it. You get some sort of vague idea what the output might look like. but it's not exact. So that could change slightly, and if people were relying on the precise behavior, it's not covered in the contract. So just something to think about. All right. So here we have a contract, and the question is there any undefined behavior in this contract? I'm sorry? Well, yeah, I'm saying, but so the question, you're saying yes, there is? Okay, so the answer is yes, and this is a kind of a giveaway, right? The is undefined unless. So yeah, there's clearly a possibility of undefined behavior. This is a narrow contract, and there's a possibility of undefined behavior. So now, how about this one? Is there any undefined behavior here? What's the undefined behavior?
If the original date is undefined because of some error of the previous concept.
So let me ask, so what was said is if it's undefined because of some other undefined behavior. Okay, once undefined behavior occurs, all bets are off, no matter where it happens, forward and backwards. So we have to talk about just this, because if there's already undefined behavior, forget about it. So this is good. What?
That's not good.
Oh no, it's not. It's not good. Undefined behavior when it occurs is not good. But
No, but if I'm doing fault-tolerant software, I have to recover from undefined behavior.
oh, okay. What you just said is not possible. So hold this one. This one I'm actually quite sure of. If you let me go through this point. When you're writing fault-tolerant software, which we are not doing here, we aren't. If we're writing fault-tolerant software, then you can't do it on one platform. You have to do it on completely separate platforms, and they have to be independent and spatially apart. But that's not the purpose of this talk. Okay, I understand. This is why we had this wonderful chance to meet each other back in, what was it, 25 or years ago? Anyway, so hold off on that. Anyway, the point here is that we have an invariant on the object. And the invariant is that this object will represent a valid date. It will. That's what will happen. And the interesting question here, and keep in mind that this is library software. It is not facing an intoxicated front-end user, right? We're dealing with people who presumably are calling things properly. So, given this, I want to ask the question, must the code itself preserve invariance even if one or more preconditions of the method's contract is violated? I hope everybody understands that the answer is no. Number one, it's impossible in general. Number two, even where it is possible, it can be prohibitively expensive. I'll give you an example. I have a logarithmic search, takes 2 iterators. The precondition is that the range that those iterators refer to is sorted. I hope everybody knows that I can't verify that the range is sorted in less than linear time. Therefore, if the condition on the function is it executes in logarithmic time, then if I pass it something that's not sorted, it will fail. And there is no way to fix that, short of breaking the postcondition, the essential behavior. So I just want to make it clear that this is not my opinion, it's just a fact. So since it's not always necessary to do, let's keep an open mind and say it's not necessary to do. We have to rely on the client to call the function properly. And that is the way things happen. And when behavior is undefined, it really is undefined. Anything could happen. Turns out that works out very much to our advantage, which we'll talk about a little bit more. So design by contract. If you give me valid input, I will behave as advertised. Otherwise, all bets are off. Okay, just want to point out in our code base, we state what goes on in this order. We say what it does. And the first line of any documentation for a function will say, what the function does in the imperative. What it might do is return something, in which case we just leave out the first one and say that what it returns. So that's what it does, then that's what it does. Then additional essential behavior is discussed. It turns out that the voice on that changes from the imperative to descriptive. Next, the behavior is undefined unless, not if, but unless, and when we list out the things that have to be so, otherwise all bets are off. And then finally, the note that, we say note that at the end, if there's something to say that is not normative, meaning it's not part of the contract, but it's just for clarification, because somehow either we weren't able to quite get it out in the contract clearly, or we have some additional suggestions. This is what every single function level contract looks like in our code base, and it's extremely valuable because you know where in the doc to find what you need to find to do what you need to do. It's also not like Java doc. It really does read much more like English prose, which I find much more satisfying than having a sentence for each parameter that doesn't relate to the other parameters. So this is very important to me, and it's different from what a lot of other people do. All right, verification. How do we, as users of a library function or library whatever, how do we make sure that we're calling that function in contract, satisfying its preconditions? How do we do that? Or at least what's an essential part of doing that? You have to know what the contract is, which means you have to read the manual. Okay? If you don't read the contract and you call it out of contract, it's on you. Now, there's more to it than that, but in fact, one of the things we want to be able to do is in certain build modes, we want to be able to detect the subset of what we tell the human being that is detectable and do something about it, which goes to Jim's point, right? Because if something goes wrong and you're in a mode where you're trying to be more tolerant of the caller of the function, you might be able to do something. And I can give you an example where that is a reasonable thing to do. I'm writing an editor. I've got, I have an editor. I've written an editor as an application, and I'm calling a perfectly valid library, but I made a mistake. So I called something and it's bad. Normally what would happen in that particular case is it would dump core. But because I've installed this special kind of assert, which is something that we're working on in the standard and already exists in our libraries, in the right build mode, it will do whatever the owner of main said to do. So if the owner of main said, I want you to save this file in save this data in some temporary file and then exit, it will do that. But there's no guarantee, remember, because it's out of contract. But we have this wink where we say, okay, yeah, but in this build mode, we'll do what we can, but no promises. Yep?
Would you only try to assert when you can afford to assert?
No, they're actually, the question is, would you assert only when you can afford to assert? It turns out that there are two different kinds of asserts being considered. One of them is anything we can do that doesn't violate the big O complexity, but that one, and then there's one that's more than that. So that one is kind of like asserts are on, and then there's another one called audit. Think of it as, okay, we're taking away all of the runtime complexity postconditions or essential behavior, and we're saying, do everything that is almost at all possible. Like obviously if it's going to run in exponential time and it's going to die, don't do that. But if it's doing something that might take a very, very long time compared to the other one, but still doable, do that. Now, because remember, there are some things that we can check that we would never check because it's ridiculous, it's absurdly expensive, So those we wouldn't do. But there are two levels. So the level that we can do, and then the one that exceeds the big O. Fair enough. Now, this is called defensive programming. This is what I think of when I talk about defensive programming. It lets me defend against client misuse. Okay? Postconditions. What do we do to make sure that our library components, given good input, return what we said they would do?
So, I have a question.
Yeah.
On your previous point.
Yeah.
When is the assert going into the standard?
When is the assert going into the standard? Okay. We don't know because it hasn't been designed yet. I have been working with a small group of people, including Bjorn Strustrup, to come up with a unified contract assertion proposal. In that proposal, the contracts can be either in the interface or in the implementation. In my design in the library, they're only in the implementation. That's all that's possible without language support. Oh, so that's that. In my version, the one that we use at Bloomberg, we have more levels than 2. We have 3. And technically, I think we started out with 4, and 4 was too many. And 3 might be okay. The 3rd level, by the way, is leave these things on even in production. In other words, they're super cheap and important, right? The difference between the other 2 is very clear. It either satisfies the contract or it doesn't. And on the other side, we're saying this is so important, I want to leave it on even in production. But the idea there is that the cost is so small that to be negligible. Anyway, so to answer your question, it could be 2019 or 2020, could be, but I can't promise because it's a standards committee. It's not my committee, so they go at their pace. Geologic sometimes, but okay. All right. So postconditions are to answer the question that I was on before. Postconditions, you test them by a component level test driver. That's the only way. What are you going to do? You're going to test your code. That's cool. What about invariance? How do you test invariance? After use. So how do you do that? What does it mean to test after use?
You would make the invariant is part of the precondition, so you can execute the preconditions, but it's also part of the postconditions, so you need to check them also the test driver.
Okay, invariance, let me just explain what I mean by an invariant. An invariant of an object is true after the object has been constructed, before it has started to be destructed, and in between calls to public member functions. So, when I start to call a public member function, the object is satisfying its invariance. For example, in a vector, the capacity is always no smaller than the size. That's an invariant. Now, when you do pushback, you're in the middle of a function. The invariant might not hold, but by the time you come back from pushback, that invariant will hold again. Yep, Jim.
This seems to imply restrictions on what one public member function can invoke among the other public member functions of the same class for the same object.
Right, and they're
This is what I feel.
okay. I understand the point. Let me just try to state the point. It would, if you do this, it would stop you from calling a public member function from another public member function, because it's possible that public member function invalidates the invariance, right? So the note here is, don't have a public member function call another public member function if the first public member function doesn't have its invariance in line. That's number one. And the way you fix that is, if this case happens and you want to call that function, you have this one call a private function that doesn't require the invariance. You have to somewhere in this world, you have to be, again, you're levelizing what's going on. And this is just the definition of an invariant. This is not the design of a language, right? This is what an invariant means. If you have a public member function, and you have an invariant, then this is what is true before the public member function is called.
Externally.
Okay.
So it's called externally.
Okay.
You call it internally.
Yeah.
You are in the mutation.
Okay.
You don't obey the rules.
Okay. So what was said if it's called internally? I understand that. Then It's on you as the developer to make sure that the code doesn't break. That's ultimately the idea. Whether you do it by forwarding to the part of what you need to do that isn't going to break the code to a private method or whatever, that's all up to you. If it turns out that you look at the code and say, hey, this is going to work fine, then it's going to work fine. Then you test to make sure it works fine, and it works fine. I'm not trying to specify how you do it. I am trying to ask, how do we test invariants? And invariants are notoriously hard to test. And that's why I'm giving a suggestion. Yes?
But also, if invariant is part of the contract,
Yes?
between the class and the client, consequently, invariant doesn't apply to the class itself, because
Right. Well, we're saying again that if somebody who's designing the class wants to look inside the implementation of a public function and say this is going to work, then fine. Again, that's your own method. That's the way you solve this definition. But the definition still stands, and the point was made that if it's a public client, yes, that has to be true. If it's a private, internal, then that's your development methodology. I would try to avoid it for maintenance purposes. I hope at least that's fair. I would try to avoid it. All right. And invariance, the way we test invariance, there is one function that every object goes through in its lifetime. What is that one function? Destructor. So if we put the assertions of the invariance in the destructor, and then we go through a thorough testing process, then what's going to happen is we'll bring the object to every state relevant for thorough testing. And then when that object is destroyed, goes out of scope, whatever, this assertion will occur in whatever build mode we've decided is appropriate, and then if something's wrong, it'll let us know. So that's how we do it. So this is the three ways that we verify our assertions, or excuse me, our contracts.
what about functions?
What about what? What about functions? Well, the functions are either on an object or they're not. Now, I'm thinking of the state as being part of the object. There are people that have global state. I don't talk to them much, but they do. And you have to work that out. But I'm really talking, right? No, but I'm talking about typically objects and free functions. Yes.
How are going to happen with preconditions and postconditions outside of a wrapper before and after the preconditions?
How about the preconditions out? I'm sorry, I'm not getting it. Have the preconditions.
You take out your precondition definition into a class.
Yes.
And the constructor and destructor.
Yes.
And that's a wrapper around the actual function call.
I think let me see if I understand this correctly. You want to create, is this for testing invariance or is this for testing something else?
It's for writing very simple preconditions.
Well, the preconditions for each function will be different. Why do we need, I'm not sure why we need a wrapper. What we need to do is on entry to the function, we need to verify that the things that we can and choose to check are just so. So those are preconditions, but have to be for each function, not put them in one place and check them, just call the function, right? Right, so that would work if you wanted to check invariance at the beginning and end of every function. You'd say, here are my invariants, and then you would call them at the beginning of the function to check, and you call them at the end of the function. You could do that. I think that's overkill.
So the invariant of the class is pretty much precondition to any function on the class. Because you need
That's correct. Right, so
you actually do not assert in every function that the invariant
No.
is true, because once you constructed an object, give the right usage, you have a valid object, and any public function calling that object will produce again a valid object.
yes,
So by proper use, you will not get to a state that violates the invariant.
that's the idea.
That's the assumption.
But there's also the fact that people are fallible. And so this is a way for writing code even in the presence of faults by people, right? If a person who's coding makes a mistake, then you want to catch it. I'm saying that by putting the assertions in the destructor, we get most of the value without making two calls to this function for every function we call. That's just overkill, again, in my opinion, because the other one works. Right? If you have a problem and you solve it and you're happy, don't keep solving it. Just move on, another problem. Okay? All right. Preconditions always imply postconditions. So there is a rule, and this got actually brought up in the discussion with the standards committee. If there's an assertion failure, if we detect what would become undefined behavior, there was a statement that no way are we allowed to return normally. And that sounds like a really good rule until you're in a large corporation where people haven't been using this, and you start to install these, and you get all kinds of assertion fires, right? They're just going off like nobody's business. So it turns out if you're in that state, and I expect many people are, you won't be able to get to the new state, which is that none of the assertions are firing, because every time you try to add an assertion, you bring things down in production. So the awful secret is you have to log this undefined behavior and let it continue the way it did yesterday, right? And then you send tickets to people and say, you messed up, fix it. And then when everybody's fixed it and there are no more assertions firing, then you turn it and say, now if it happens, bring down the program. And then you have a clean assertion build in life. It's good. But to get to that state, you have to first do a little bit of monitoring, and some purists will say, there's no way I can ever return from a precondition failure because that's heresy. That's the worst thing in the world. And then the engineers will try to convince that person that, but you want to get to that better state, and to do that you have to return after logging. So anyway, this is the theoretical answer. All right. Abort should be considered, especially when you don't have exceptions enabled. It's much better to not continue. Now, this became very clear when Knight Capital went on for like 40 minutes and lost hundreds of millions of dollars because somebody didn't stop it. And so it's much better than just going headlong and whatever to bring down the program in almost all cases. Especially in we need fault-tolerant things in fighters and whatever, but that's handled not by this. That's handled by having redundant systems that are separate. All right, and good library components are what we call exception agnostic. I say exception agnostic rather than exception safe because the way we do it is we don't rely on catching and rethrowing and doing anything like that. We use a variant of RAII, resource acquisition is initialization, but in our world, rather than throwing from a constructor, we acquire the resources and then guard them until we give them back. But other than that, this is a much safer way of doing things, and you don't have to worry about the words try and catch and throw. You don't have to deal with that because it's handled for you by just careful normal design using a standard string or a standard vector or whatever to manage those dynamically allocated resources. Okay, so we are now up to questions for this. Any questions? I'll just put these up so you can take a quick review. Yes?
When you call some functions, the state of the object might not change. When you call some other functions, they might change the state of the object.
Yes.
Is the invariant you were talking about, it should be invariant when during any call to a function?
Okay, the definition of invariant, slightly amended, but I'm going to try to just say it for sure that we can all agree on, is for any function. Now, if it doesn't modify the state, that's great. But if it does modify the state, it'll put it back in a condition that satisfies the invariance before it returns. Okay? If it doesn't modify the state, it doesn't have anything to do, because it didn't change anything. Yes?
That brings up another thought. In the early days of C++, we distinguished between physical constants and logical constants. You calculate constants.
Yes. So
you can have functions that give all the publication and the reason of having those side effects when, in fact, they did.
okay, so the point is, it's actually the footnote goes the other direction. Now we have threads.
Yeah.
And so all of that logical, physical mumbo-jumbo went away, because now if something's const, then it's const thread safe, that kind of thing. Something is const and isn't thread safe, you run a problem.
Yeah.
So what we do now, today, not when you wrote your book, which was a long time ago, now we don't make a function const unless it's physically const. And that's why the string implementation changed and broke everything, because we used to have a copy on write in some, right? And we don't have that anymore. Why? For the very reason you just talked about. Okay.
So that means no mutable.
Now, mutable, we do need mutable, but we need that's part of threading, right? But we need to make it clear when something is mutable, we need to state it in some clear way as part of the contract. You got to know this. You can't keep it a secret. If you have a function that's declared const and it's not really const, then you better say in the contract of the function, oh, by the way, it isn't const. I was lying. Okay? You have to. Otherwise, I'm going to assume it's const, because that's almost every case. Okay? Okay. Any other questions?
All the contracts you're sharing are written in comments and not in text.
All of the contracts are in,
Comments.
you say comments. I like to call them documentation, but yes, they're in English, yes.
They can instead be in text
In
and
code. Okay, so this brings up a good point. What is being asserted is that there are some ways, sometimes you can say something that is in English in code. That is true. It is not always true. So let's say I have a requirement that one of the arguments is not 0. I can easily write code to verify that, right? Right. But suppose I tell you that I'm a library and I'm saying something like, you must have called that function before calling that function, and then you must have pressed this button. Otherwise, the behavior is undefined. But you have no way of knowing if the person did that. You have no visibility into the history of the program. So there's no way to write code to check what happens outside the call to the function. Do you follow what I'm saying? There are certain things you can tell a person who has more information than the library component. You have to do this first. There's an order of things. You have to do it this way. But you may not be able to check it. Even if you were a human being sitting on the other side, you'd have to get outside your component and go ask the caller a question. I don't know if I'm making this clear. You cannot always programmatically check if what you told the client to do was done. Yes?
So I kind of think you get caught kind of between Scylla and Charybdis, because if you really could programmatically check, if you decided to enhance the language.
Which we're doing.
Or it's undesignable, in which case it's unenforceable and can't be part of the contract anyhow, because you can't design it into your code.
When you said unenforceable, the contract is saying, if you happen to do this, I will work. If you don't happen to do this, I no longer promise to work. But I don't have to check it.
But I mean, if, for example, if at some time in the past you have called this function, before calling this function, I promise to behave well. If you have never called this function, I mean, I do not know of a good design regimen that will allow me to design to guarantee that precondition. And so it's a great way to cop out.
Well, I'm into copping out when it makes engineering sense.
I don't think that, I'm an engineer, and that doesn't make sense.
Okay, and we have markedly different philosophies on this, but the way the standard is going is more like what I'm saying than what you're saying.
I understand. Are you looking for any input on the standard?
I'm happy to take input, but I'm only one person on the standard. Okay.
Do I need all of you in the room at the same time?
Pretty much.
There you go.
Okay. That's how we got as far as good. Frank?
So I guess as an example, suppose you have something like placement new,
Yeah.
where you need to have a valid pointer,
Uh-huh.
point to some memory,
Yep.
but there's no object.
I was going to bring that up next. So your point is, suppose I wouldn't put this in the contract because it's obvious. But if you pass in an object that hasn't been constructed and expect it to work, good luck.
Yeah.
How am I going to check that?
That's the reverse. You could also require that there must not be an object yet, because I'm going to construct one right there.
And that's interesting too. Right, in other words, you have to know whether there's an object there or there isn't. If there's an object there, you're going to wind up leaking memory. Is that your point? Because you're going to clobber it.
That's undefined behavior.
No, well, it's not. It's actually not, believe it or not, it's not undefined behavior to leak memory, and it's not undefined behavior to clobber an object with another object. It's not. It sounds like it is, but it isn't.
Okay, but you cannot easily check it.
No, it's not only, you can't check it. This is what I'm trying to say. There are certain things you can't check, but you better not do.
And that's an example.
And that is an example. Jim, do you want to respond?
I don't know if this is just one definition backing another. Well, it sounds like it's undefined behavior, but the standard analysis said it is not.
It's not undefined behavior unless you try to use that object after it's been clobbered. Then it's undefined behavior. But just clobbering the object, no problem. That's how allocators work, by the way. When you have an allocator and you allocate a bunch of objects and then you say, bye-bye. If all the memory came from the allocator, you don't even leak memory. They just don't exist anymore. If you don't try to use them, you're fine. Now, if you try to use them and in a function that says don't use winked out objects and you'd go ahead and do it anyway, you're out of contract, but I can't check it. I think that is a great example. It's one of many. We could sit here all day and find things that you can tell people not to do, but I can't know that you didn't do it until the computer catches fire and burns. Okay? Please trust me. There's what you can check reasonably, what you can check at all, and then what you can tell the human not to do. Those are 3 levels.
I guess where maybe our main philosophical difference is, again, coming out of fault tolerance, using words like it's computationally reasonable, that within some parameters, a big O, we're allowed to do this.
Right.
With respect to, is this goal-like somewhere? What is computationally reasonable mean? What does big O mean? And Preconditions article to the contrary, notwithstanding about the meaningless of big O.
Mm-hmm.
There just seems to be a lot of arbitrariness here and a lot of kind of pants engineering thinking, which...
Okay, I agree with you that there is some fuzziness, but there is also some mathematical validity to it. We know that we can do binary search in logarithmic time in the number of elements. That we know. We can then say it is a requirement on this object that it do so in logarithmic time. We know that. There is a mathematical certainty that we cannot check it in less than order n time.
Right, but Conan's point, for example, is that if you look at order of n and n log n, they cross over at some point. And if there's only 4 objects in there you're dealing with,
Yes. Okay. What you're saying is linear search is faster than binary search for small n. Great.
so why isn't the size of n also part of the assertion considerations? I mean, why just make a blanket statement based on computational complexity?
I'm saying if you do. You don't have to. You could just say, I don't have any restriction.
What I'm trying to understand here is that you've made some statements saying, this is particularly with respect to the assertion, that we're not going to try to protect the programmer against their own behavior if the alternative is computationally intractable or too large or something like that.
I think that's yes.
Who makes that decision?
The person writing the library. And they have to decide whether they're going to do it at all, or they're going to do it in an audit mode, or they're going to do it in a regular mode. That's the choice of the developer.
But they can use the face of the moon for making the choice if they desire so. It really doesn't have to do with computational.
There's something called quality of implementation.
Yeah.
Okay, that's where it comes from. You have to make good engineering decisions. All right, I'm going to move on to the last section. I appreciate all the comments. I will take them under advisement. Now, narrow versus wide contracts. This is really live stuff in the standard, by the way. There's a small group of people that are really trying to come up with something that enables people to do what they choose to do, whether it be in the interface or the implementation or whatever. We're not telling people exactly how to use it. That's not the standard's job. We're trying to come up with an enabler so that people can use it. And it does have some very important and good uses. It does improve code. It detects bugs. I mean, it's a good thing. It is not the silver bullet that solves all problems, though. It is just another thing. So, narrow versus wide contracts. I want to specifically focus on what happens when we have narrow contracts. So, first we need some pejorative terms, okay? So, fat interface. We know that's bad, whatever it means, right? We'll talk a little bit about it in 4. We have large or non-primitive interface. You know, that's when we start to take something like a string class that's supposed to be a string class, and it stores a string value, and we put everything in the kitchen sink in it, like, what was it, in our string class back at Mentor, I felt like, what was it, name is name of famous actor. You know, that function was probably not necessary. Is palindrome, does it really need to be part of the string class? So anyway. So the third one is a wide contract. This is a pejorative term. Wide, I say it because, you know, people like everything to be handled. Now, Jim, I think, would be in favor, if it could happen, that every contract would be wide, and you know what would happen no matter what you passed in, whether it was unaligned memory or who knows. It would do something, and you would know what it is. I can appreciate that desire, but that's not C++. So, C++ has narrow contracts. What should happen if I pass 0 into strlen? Okay, it could be. Sure, it could be. But is it a good idea?
You have the knowledge at compile time that something is wrong here. Why are we talking about anything beyond that?
Okay, what I put the 0 there, that is a literal 0. It could be something where you don't have knowledge at compile time. So the answer, is it a good idea or a bad idea, is this becomes wider, but it's still not wide. Why? Because even if I say, if it's this, return 0, what about if it's not null terminated? And I'm waiting for Jim to tell me how we're going to detect this one. Suppose it's not null terminated, and I say, please pass in a null terminated byte string, right? Suppose it's not null terminated. How do you check that? You check that by letting it go off the page and core dumping. Then somehow you catch that signal, okay? So there's another example of where you tell the human being, please pass in a null terminated string, and if the human being doesn't do that, they pass in a non-null terminated string. What are you going to do?
So in real fault tolerance, you would never do that because what you just asked for is arbitrarily uncomputable. It's NP hard. And the compiler is not going to enforce something NP hard, and you're going to...
I don't see where...
What we'll say is there has to be a null character within, say, 1024 bytes.
Okay.
That's computable and has a fixed cost, which we can evaluate. And so, I mean, that's a reasonable thing.
What if you go off the page before then?
That also we handle, but at a lower level.
Okay. So I'm talking at this level. I wanted to point out that there are things you can tell a human being easily that cannot be easily checked. Is that fair?
I say that if you are working at that level of code and have access to this, there's something called the Brewer's Law, which is you will be bugged at the lowest accessible level of technology. And if you have access to that level of technology on this side of the abstraction boundary, you're accountable.
Okay. Again, I'm talking at the C++ source level. Frank.
If you're going to try write a component that has something like a string function that checks maybe maximum string length must be within 1024 characters, and then you're going to try to use it in a larger system where you need to increase this constant because you're using larger strings, then you need to reconfigure this component or have it duplicated or whatever, and you end up with all sorts of
And it also...
configuration.
Yes, there's that, and there's also the tremendous overhead of checking 1024 characters when your typical character string size is 10. So, to one side, in real engineering, no one would ever do what you're saying.
Oh, we do it. I'm sorry.
Okay, don't be sorry, but no one in my area would ever do it. All right, let me move on. You have paid me back with interest, okay? All right. The real problem here is it's likely to mask an error. We don't want to mask an error. You raised your hand in the back. Did you? What you're saying, I think, is in a safe mode, in something that we do checking in, you'd like to detect that this is 0. And by the way, the other reason not to do this is more code runs slower. And it's worth pointing out that even code that doesn't execute is still in the instruction stream and can slow things down. Okay, so I'm with you. Hold on. How about this line? Can that line exist? See, what this is, it's saying it's a narrow contract, and if I'm in a debug build, it will blow up. If I'm not in a debug build, who knows? It's undefined behavior. So just don't call 0. You can just don't pass 0. You can tell a human being, just don't pass 0. If the human being passes 0, you have a problem. You also tell the human being not to erase the object by mem setting it to zeros, right? But if the human being does that, what are you going to do? You can't tell. The object cannot stop itself from being written over by a rogue, copy. So. Yes, well, you can turn them off. You can turn them off by just building it differently. There's no checks at all. That's what makes defensive programming possible. Because if you put defensive checks in everything, the code will run horribly slowly, and then you won't use it. So it's important to be able to wink them out. Another way people used to do this, Drewstrip has something called a checked or a vector, where the derived vector, the vector derived from the STD vector, does the bounds checking for the brackets. The trouble is, when you pass it through into a function, you get the slicing. If it takes a vector, you get the slicing, and so you don't have the nice advantage of having it built in to the vector. If I were implementing an STD vector, there would be my own kind of asserts in the bracket function that would be active only in the appropriate build mode. So here's another example. We have set date, and it takes 3 ints. Should this return status? Because maybe the dates aren't valid. Now, this is a design question, right? What do you think the answer is? Okay, absolutely not, because what happens is, here's my birthday, 3/8/59. I know it's my birthday, so I don't need to check anything. So I'm not going to check the status, and now it turns out that I should have called it this way because this is the right order of the arguments, and oh, by the way, I didn't put in the first 2 digits. So if I'm doing a check and returning status, I've turned this into a wide contract, and there's no way to mechanically verify what I'm doing in any build mode. So this is a double fault. You can't guard against double faults. So it's much better to have the possibility of turning on checking and catching the error than relying on the human being to get the thing right and check the status. And if the status is bad, what are you going to do? Now, in this case, it's very cheap to set this kind of date, right? If I put this assert in, it becomes very expensive because the cost of the isValid function completely overwhelms what's going on in the regular work done by the function. But now I'm checking it only in a debug mode, so I can turn it off. All right. Now, right next to that function in the class, there's going to be a set date if valid. This is a convention, a conventional suffix that we have, so that if you don't trust the date coming in and want to check it, and if it's good, set it, you have this function. Now, we can have the 2 functions side by side, and you'd really have to be a bit crazy to see set date if valid and call it instead of set date and then still not check the status. That would be a little nuts. So we have both of those together. Now you do what makes sense. All right? This is wide contract. It's checked in every build mode, which means it's slow, but sometimes if you don't know if the data is good, you got to check it. All right, what should happen? Yes?
How do you make this kind of code coexist with libraries that do return status?
Okay. Okay. So let me go back here. This does return status. So in this one, it's a wide contract. This other one doesn't return status. So it has, right? It has a narrow contract. So you have both functions. Then as a client, you have to decide which one are you going to call. If you know the data is valid, you call the one that returns void. Then if you're wrong, I can check it in a checked build mode. If you call the other one, you better check the status because I'm not going to do it. Okay? Oh, okay. All right. So next one. Here's operator bracket. That has a narrow contract, right? Here's the at function. Is the at function, does it have a narrow contract or a wide contract? It's wide, absolutely. Because if you call the thing outside, it's going to throw an exception, but that's part of the contract. So everything is handled, right? This depends on the build mode. This is essential behavior. So it's wide. I hate this function. I hate it. I'd much rather have the option of checking in the square bracket one because I can have it on or off depending on the program and the time of day and whatever I want. Okay. Here's an insert, and I've got an index and a value. I was having this conversation, I think it was circa 2000 and maybe 2003 or 2004 with two people actually in the UK over the phone. And they suggested some very interesting things for this, like what should happen. What do we do if the index is greater than length? One of them suggested that we just move it to the beginning, kind of like a Perl or something, I don't know. So if you made it less than 0, just make it 0. Or if you made it longer than length, just make it length. So that was the suggestion from one of them. But the other one, you won't believe this, take the absolute value and mod it by the length plus 1 so it goes arbitrarily into the array, all right? Now, I couldn't stop laughing, you know. But people actually say this stuff. So anyway, more code runs slower. This would just mask defects. This is undefined behavior and should remain that way. And no, we're going to do this. We're going to assert that you didn't get it wrong, and if you got it wrong, we're going to let you know. And when I say this assert, I really don't mean this assert. I mean the special assert that will eventually be provided by the C++ language that will say, oh, if this happened, do that. And the do that is whatever the owner of main said. So that's the real answer. This is just a stand-in for that. Okay? All right. So if you want to see how we can do this today, go look at BSLS assert on GitHub in the BD libraries. All right. This, by the way, is open source and usable. It's very useful. It's the most heavily used component I know of on our stuff. Okay, narrow but not too narrow. This is just an example. Suppose I'm trying to write a function that replaces some range of elements with a particular value. And the number of elements could be small, large. It could be the entire length, or the number of elements could be 0. So what happens if I'm trying to specify an index that's equal to the length of the array, and the number of elements is 0? That's a no-op, right? Now, I could certainly copy all 5 elements, right? I could start at 0 and go all the way up to 5. That I could do. But if I go the other way, could I have 0 elements but copied at the end of the array? Do you see what I'm saying? I'm wondering if this makes sense. So this might be, we might look at the one that does nothing and say, we don't need that. Let's make that undefined behavior. Who would ever do that? But as it turns out, if you try to make that undefined behavior, you run the risk of someone on the other side having to check it first. And if that happens, you're getting more code. So here's an example of what the assertions would look like for this. 0 less than index, 0 less than num elements. index plus num elements less than or equal to length, you would have to go out of your way to check this last thing, and then somebody else would have to go out of their way to check it on the other side. So it turns out we wouldn't do this. We would just say, that's fine. You're not going to try to make it as narrow as you can. Should make it narrow to the point where it obviously has clear meaning, and it doesn't require more code to solve it. Now, obviously, if I passed in something that's off in the fifth quadrant, you know, or off in the first quadrant, all the way over out here, that's you know, that's not a good idea. Then you're making up functionality you don't want to make up. So now the client would have to check for this. So more code runs slower. Again, we want to, if you don't have to do anything extra to make it work, if it's obvious and intuitive, and there's no possibility of ambiguity, leave it be. So it's natural to just let it be there. All right. So we are getting close to the end of the first part, because I hear lots of people clapping. So I'm going to put up these questions, and after these questions, we are done. So you can ask as many questions as you want, if there are any. Yes? Okay, I didn't quite understand the question. If you have the pattern, which one is it? What are we talking? Are you talking about this? Oh, yeah, set day. Okay, yes. No, I don't. I don't do that because it's the client's code base. I'm a library, right? That's the point. You want to do defensive checks that the client can enable that make sure that the client didn't call you out of contract. That's what defensive checks do. That's why this is not necessarily a good thing, because we can't help you. At least, look at it this way. Suppose you're the person who's running the project. You have 5 guys working for you, and they're kind of shoddy. You know, they don't always do what they're told to do, like read the manual. So then you call me up and you say, John, I want you to check that they did the right thing to the extent that's possible. And I say, okay, great. So we have asserts built into our code. You, up top, you say, okay, guys, I want you to build it in a safe mode. Okay? Then you install a handler that particularly does what you want it to do in a global place, and then if they ever call something out of contract and it's checkable, we will do whatever you said to do. Right? That's what we do. That's a very important feature. It's not going to solve everything, but it's an important one. Anybody else? Then, I guess we are done. Thank you very much for coming.